Welcome to the Deep Dive. Today, we're tackling a really specific and sometimes a tricky part of the SAT math section. We're talking about the student-produced response questions. You probably know them as grid-ins.
Right, the ones where you bubble in your own answer. No multiple choice options to save you.
Exactly. You don't pick A, B, C, or D. You actually have to generate the answer and fill it in correctly. It feels high stakes.
It can, yeah.
So our goal today is to really break these down, make you feel confident, and give you a full guide based on the official materials.
That's spot on. And the biggest difference, like you said, no options. This means you absolutely need to know your stuff, get the right answer, and know the exact procedure for gridding it in.
Precision is key then.
Absolutely paramount. You could solve it perfectly, but a tiny mistake in bubbling means no points for that question.
Okay, let's unpack what these things actually are. So they're math problems.
Right. You solve them like any other math problem.
But instead of choosing an answer, you write your numerical answer in these little boxes.
At the top of the grid.
And then you fill in the corresponding bubbles below on this special grid.
Correct. And they show up in both math sections, right? Calculator and no calculator.
Yeah, both. So
Right.
you can't really avoid them. You got to know how to handle them.
And that grid structure is, well, it's critical. Writing the answer in the boxes at the top, that's helpful for you, but it's not what's scored.
Okay. So the written part is just for clarity.
Pretty much. It's the bubbles below that must be filled in correctly. That's the only thing the scoring machine reads. No bubbles filled in correctly, 0 credit, even if 3.5 is sitting right there in the boxes above.
Wow, okay. That's non-negotiable then. And the grid itself, how many spaces are there?
It's got 4 columns, so you can grid answers from, say, 0 up to 9999, or decimals or fractions.
And if your answer is just like 7 or maybe 12, it doesn't fill all 4 columns.
That's fine. You just leave the unneeded columns blank. And you don't have to start in the leftmost column either. You could grid 7 in the second column or the third as long as the bubbles match.
Okay, flexible on placement, but strict on the bubbling.
Yeah, exactly.
So this is where those little details can really matter. What are the absolute core strategies and, maybe more importantly, the specific gridding rules people need to know?
Okay, yeah, let's get into the nitty-gritty. These are straight from the official SAT study guide, kind of the remember this list.
Okay.
First, big one. Your answer will never be a negative number. Never, ever.
Really?
Never for a student-produced response. So if you calculate something and get, say, -5, stop.
Okay.
That's your signal. You've made a mistake somewhere. Go back, check your steps, check the question constraints. It's like a built-in error check from the test makers.
That's actually super helpful. A silent guardian, as you said earlier.
Huh.
Okay, no negatives. What about fractions and decimals? That seems like where it could get complicated.
It can seem that way, but the rules are pretty accommodating. You can use fractions like 7/12 or 23. Just use the slash bar bubble.
Okay.
Or you can use decimals, like 2.5 is fine.
Right.
Or for that 23 example, you could grid it as 0.666 or 0.667. Both are accepted.
So for repeating decimals, you just fill the grid.
Fill the grid as much as possible. For 13, you'd grid 0.333. You don't need to round unless the question specifically tells you to round.
And you mentioned 23 could be 0.666 or 0.667.
Right. Either is fine. The system allows for that slight variation at the end for repeating decimals. But here's a critical point. If you get a fraction that's too long for the grid, like, I don't know, 1236.
Right, that wouldn't fit. 1, 2, 2, 3, 6, 5 characters.
Exactly. You must reduce it first. So 1236 becomes 13. Then you can grade 1, 3, 3, or you convert 13 to its decimal, 0.333.
Okay, so reduce fractions or convert to decimals if they don't fit. What about leading zeros on decimals, like 0.5?
Don't grid the leading 0 unless it's part of the number, like, say, 10.5. But for something like 0.5 or 0.333, you just start with the decimal point bubble. So grid 0.5 or 0.333. It saves a column.
Gotcha. Be as precise as the grid allows, basically.
Precisely. And another huge one, no mixed numbers.
Okay, so if I get 3 and 12.
Nope. Can't grid that. You absolutely have to convert it to an improper fraction, so 72 or its decimal equivalent, 3.5. Either 72 or 3.5 is perfectly fine to grid, just not 3-12.
Okay, good to know. What about symbols? Dollar signs, percent signs, degrees?
Ignore them for the grid. If the answer is $500, you just grid 500. If it's 25%, you grid 25. The grid is purely for the numerical value.
Makes sense. And what if somehow a question has 2 right answers, like maybe X could be 2 or 3?
That's rare, but possible. If it happens, you just pick one. Grid either 2 or 3. Don't try to put both.
Okay, just one answer needed.
Yep. And a mechanical rule. Only bubble one circle in any single column. Seems obvious, but under pressure.
Right. Easy to make a slip. And guessing. Penalty or no penalty?
No penalty for wrong answers on grid-ins, same as the rest of the SAT now. But unlike multiple choice where you might eliminate choices, guessing on a grid-in is really tough. If you have absolutely no idea, it might be better to just skip it and save time rather than plugging in a random number.
Okay, that covers the rules. Makes sense. Now let's maybe put these into action. How about some examples, starting with the no calculator section?
Great idea. Let's look at how these rules apply. First example, say you get a quadratic equation. A squared plus 14a equals 51. And the question adds, it must be greater than 0.
Okay, standard quadratic setup.
Right. The skill is solving quadratics. Best strategy, get it into standard form. A squared plus 14a minus 51 equals 0.
Set it equal to 0.
Yep. Then you try to factor it. This one factors 2, a plus 17 minus 3 equals 0.
So solutions are a to 17 or equals 3.
Exactly. But remember that condition. A must be greater than 0.
Ah, right. So the answer has to be 3.
Correct. You'd grid in 3. That condition is key. They test if you're reading carefully. There's sometimes an alternative way too, like completing the square, but factoring is often fastest here.
Makes sense. Paying attention to those constraints is crucial. Okay, what about equations with fractions? Those can look intimidating without a calculator.
Yeah, like 1/2 x plus 1/3 y equals 4. And maybe the question asks, what's the value of 3x plus 2y?
Okay. Doesn't ask for x or y individually.
Right, and that's the clue. The objective is using the equation structure. Don't try to solve for x and y. Look at what you have and what you need.
12x plus 13y equals 4. And we want 3x plus 2y.
See the connection. What happens if you multiply that whole first equation by 6?
By 6. Okay, 6 times 12x is 3x. 6 times 13y is 2y. Plus 6 times 4 is 24.
Bingo. 3x plus 2y equals 24. That's your answer right there.
Wow. Okay, so just multiply by the least common multiple of the denominator.
Exactly. It clears the fractions and often reveals the answer directly. Much faster than substitution or elimination here.
That's definitely working smarter. Okay, how about those ones where x is in the denominator, rational equations?
Good one. Say 24 over x plus 1 minus 12 over x1 equals 1. These look tough.
Yeah, they do.
The strategy is similar, actually. Eliminate the denominators. Multiply the entire equation by the common denominator, which is x plus 1 by 1.
Okay, that's going to cancel things out.
Right. It'll cancel the denominators in the fractions, and you'll have 24 by 1, 12x plus 1 equals 1, x plus 1 by 1.
Which simplifies.
It simplifies down usually to a quadratic equation after you expand and collect terms. For this example, it turns out to be x squared equals 36.
Where x equals 6 or x equals 9 is 6.
Exactly. And in this case, you'd check if either makes the original denominator 0, x plus 1 and x1 are fine for both 6 and -6, so both are valid solutions.
And since it's a grid-in, you could grid either 6 or -6. Oh, wait. No negatives.
See? That rule comes in handy. You can't grid -6, so the only possible answer to grid is 6.
Wow. Okay. That no negative rule is powerful. All right, one more no calculator type. Circle equations.
Yeah, they might give you something like x squared plus y squared minus 6x plus 8y equals 144 and ask for the diameter of the circle.
Okay, not the standard form.
Right. The objective is to find a property diameter from this general form. The key skill is completing the square.
For both x and y terms.
Correct. Group the x's by 26x, group the y's, y2 plus 8y, leave the 144 on the other side.
Then complete the square. Half of -6 is -3, squared is 9, half of 8 is 4, squared is 16.
Exactly. So add 9 and 16 to both sides. The equation becomes x32 plus y plus 42 plus 144 plus 9 plus 16.
Perfect. That's the standard form xh2 plus yk2 plus r2. So what's r squared?
R squared is 169. So the radius r is the square root of 169, which is 13.
Right. But careful, what did the question ask
Well,
for?
the diameter.
Yeah.
Sneaky. Diameter is twice the radius, so 2 times 13 is 26.
And that's what you grid, 26.
Yeah.
Always double check what the question is actually asking for. Radius, diameter, area, circumference.
Great point. Okay, let's switch gears. The calculator section. Problems might be more complex, maybe more data, but the gridding stays the same, right?
Absolutely the same gridding rules. The calculator just helps with, well, calculation. Let's look at question 5, off of data analysis 1. Maybe a two-way table showing elements, solids, liquids, gases, and metalloids, metals, non-metals.
Okay.
And the question asks, what fraction of the elements that are solids or liquids are also metalloids? Okay, reading carefully. Fraction of solids or liquids. So that's the denominator.
Precisely. Find the total number of solids plus the total number of liquids from the table. Let's say that total is 92.
Okay, denominator is 92.
Now the numerator, How many of those 92 elements, the solids and liquids, are also classified as metalloids? You look that up in the table. Let's say it's 7.
So 7 out of those 92, the fraction is 792.
Exactly. Now you grid it. You could grid 7, 9, 2, or since you have a calculator.
You could calculate 7 divided by 92.
Right, which is about 0.07608. You can grid that as 0.076. Fits perfectly.
Okay, so either the fraction 792 or the decimal 0.076 would work.
Correct, as long as it fits and is accurate.
Got it. What about unit conversions? Those always seem to pop up.
Oh, yeah. Question 6 might be about, say, transmitting images for Mars. An image is 11.2 gigabits. Data comes in at 5 megabits per second. How many complete images can be received in 11 hours?
Whoa. Okay, lots of units. Gigabits, megabits, seconds, hours.
Exactly. The objective is managing all those units and rates. Strategy, get everything consistent. First, how many seconds in 11 hours?
11 hours, 60-minute hour, 60 seconds minute. Calculator helps here. 39,600 seconds.
Okay. Now, how many megabits can be received in that time? It's 5 megabits per second.
So 39,600 seconds, 5 megabits second. 198,000 megabits. That's the total data capacity.
Good. Now, the image size. It's 11.2 gigabits. We need that in megabits. The conversions usually given are standard. 1 gigabit equals 124 megabits.
Okay, so 11.2 gigabits, 124 megabits gigabit equal 11,468.8 megabits per image.
Right. Now, the final step. How many complete images fit into the total capacity?
Divide the total capacity by the size per image. 198,000 megabits, 11,468.8 megabits image.
Which comes out to about 17.26.
But it asks for complete images, so you can't round up.
Exactly. You can only receive 17 full images, so you grid 17. Unit analysis is absolutely critical here.
Definitely. Easy to get lost in the conversions.
Okay.
How about inequalities on the calculator section?
Sure. Question 7 might give you a compound inequality, maybe something derived from a setup like 95 3t plus 174. Let's say after some steps, you simplify it down to 2120 t275.
Okay, so it's between 1.05 and 5.4.
Right, but maybe the question doesn't ask for t. Maybe it asks for a possible value of 93.
Okay, so we need to find the range for that expression.
We could multiply the inequality 2120 t275 by 9, and then subtract 3 from all parts.
Okay, 9, 21, 23 is the whole calculator time again. 9, 1.05, 3 is 9, 5.45, and 9, 275, 3 is 9, 5.4, 3 equals 48.6, 3 equals 45.6.
And the question asks for a possible value of 93.
Right, so you just need to pick any number between 6.45 and 45.6, like 7 or 10 or 40, or even a decimal like 44.25. Any of those would be correct to grid.
Okay, so find the range and pick a valid number within it.
Got it. Need to remember that inequality sign flip if multiplying dividing by a negative, though.
Always. That's a classic trap.
Okay, trigonometry next, maybe in the calculator section.
Yep. Question 8 could show an isosceles triangle, maybe label an angle x, give some side lengths, and ask for cosecants.
Isosceles. So two sides are equal. Two base angles are equal.
Correct. The key strategy, often, is to drop a perpendicular height from the vertex angle down to the base.
That splits the isosceles triangle into two congruent right triangles.
Exactly. And once you have a right triangle, finding cosine is easy. Remember SOH-CAH-TOA.
Adjacent over hypotenuse for cosine.
Right. So using the side lengths in that new right triangle, you might need Pythagorean theorem to find one side. You calculate adjacent hypotenuse. Let's say it comes out to 1224.
Which simplifies to 12.
Yep, so cos x equals 12. Now, how do you grid that?
You could grid 1, 2, or the decimal equivalent, 0.5.
Perfect, or even an unsimplified but equivalent fraction that fits, like 2, 4, 3h, all represent 12.
So multiple correct ways to grid the same value.
As long as it's equivalent and fits, yeah.
Okay, nearly there.
Mm-hmm.
How about another multi-step problem, maybe involving money or percentages?
Sure. Question 9 could be about foreign exchange. Sarah buys 602 rupees for $9.50, but there's also a 4% transaction fee on the dollars. Oh. It asks for the exchange rate in rupees per dollar, rounded to the nearest whole number.
Okay, multi-step. First, find the total dollar cost, including the fee.
Right. $9.50 plus 4% of $9.50. That's $9.51 or 4 cents.
Calculator. $9.50, $1.04 rupees, $9.88. How many rupees per $1?
Set up a ratio. 602 rupees, $9.88 over rupees $1.
Exactly. Solve for RR equals 62, 9.88.
Calculator. 602, 9.88 is 60.93.
And the question says round to the nearest whole number.
So 61, you'd grid 6 to 1.
Correct. Breaking it down into steps. Find total cost, then calculate the rate.
Makes sense. Okay, one final complex one from the guide. Maybe that prepaid card problem. Yes. Question 10. This one ties several concepts together. Sarah has 7,500 rupees on a prepaid card she bought at some exchange rate, dollars per rupee, let's call it D2R. She could instead use a traveler card that charges the dollars plus a 4% fee. The question asks for the least number of rupees she must plan to spend so that using the prepaid card is cheaper than using the traveler card for the entire amount.
Okay, that's intricate. We're comparing total costs.
Exactly. It involves setting up an inequality. The cost with the traveler card for X rupees would be XDR $1.04. The cost of X rupees on the prepaid card is just XDR dollars if X is less than or equal to 7,500, but the problem implies she wants to spend more. Let's reread that source setup. Okay. The source sets it up comparing the value obtained. So the value from the prepaid card is 7,500 rupees. The value from the traveler card for D dollars is 7 rupees per dollar. The traveler card cost is 1.04 D dollars. You want the rupees you get from the traveler card, D 1.04, to be less than or equal to the 7,500 rupees on the prepaid card. No, wait, that's if the traveler card is better. We want the prepaid card to be cheaper.
So the effective rupees per dollar on the traveler card is worse.
Let's look at the source explanation again carefully. It says, you want the cost in dollars using the prepaid method. Let's assume the initial purchase cost D dollars for 7,500 rupees to be less than or equal to the cost using the traveler card for reband. Traveler card cost for R rupees is R rupees per dollar 1.04. The initial exchange rate was 7,500 rupees for D dollars or D $7,500 per rupee. So the traveler cost is RD 7,500 1.04. You want D RD 7,500 1.04.
Okay. Divide both sides by D.
Right, assuming D is in 0. So 1.04, 1.04. Rearrange to solve for RRs of 7,500, 1.0.
Calculator, 7,500, 1.04, 87211.53.
So the least whole number of rupees she must spend for the prepaid card purchase to have been cheaper or equal per rupee is 713,212.
Okay, that took some careful setup of following the source logic.
Yeah.
Setting up that inequality correctly is everything.
Absolutely. It's about translating the word problem into a mathematical comparison.
Phew. Okay, we've gone through a ton of rules and examples. Thinking back over all this, what are the biggest pitfalls or the absolute must-do best practices people should walk away with?
I'd say 3 main things stick out. 1, always convert mixed numbers, either improper fractions or decimals. The grid simply cannot handle 312.
Right. Non-negotiable.
2, manage your fractions and decimals for the grid. Reduce fractions if needed. For decimals, fill the grid, but don't add unnecessary leading zeros. Make sure it fits and it's accurate. Don't over-round unless told to.
Fit and accuracy. Got it.
And 3, double-check that your answer makes sense. Does the number seem reasonable for the question asked? If you're finding the number of students and get 4.5, something's wrong. If you calculate an angle and get 200 degrees, check your work. That kind of basic sanity check.
Yeah, that final glance can catch simple errors.
And, of course, practice. Use the official resources, like the problems linked to Chapter 21 on sappractice.org. Getting familiar with the types of questions and the gridding process itself builds huge confidence.
So wrapping this all up, what's the big picture for someone prepping for the SAT?
Well, this deep dive into just one chapter, Chapter 21, on one question type, shows the level of detail involved. It's not enough to just know the math. For grid-ins, you have to know how to present that answer correctly according to very specific rules.
It's about both the solution and the submission method.
Exactly. We've covered the skills, the strategies, different question types from no calculator to calculator, walked through official examples, and highlighted the key tips. This gives you a really solid foundation for tackling these student-produced response questions.
Fantastic. So we've thoroughly explored Chapter 21 of the official SAT study guide, hitting all the key points on grid-ins.
We have indeed. From the basics to complex multi-step problems covering the strategies and pitfalls, listeners should now have a comprehensive understanding of this section.
And with that, our deep dive is complete. Huge thanks for joining us today on the deep dive. Keep learning, keep practicing those grid-ins, and we'll catch you on the next one.